4.5 function operations. So notice these questions do ask for the domain oftentimes. And a lot of times it's just going to be all real numbers unless there is some variable in the denominator, which is going to create, a type of restriction on the domain. Function operations can be written in two different ways. So these are the same thing. The left column and the right column have the same exact meaning. This just says I'm taking a function and adding a function. All right, so it can be written either way. Be familiar with both ways. Just means that I'm adding two different functions. Same thing with subtraction, f of x minus g of x. It just means I have the f function first and I subtract the g function, but it could also be written as f minus g evaluated at x. Multiplication, so f of x times g of x could be written as f times g, all evaluated at x. Just means I'm going to multiply the functions. The math's not new, just the notation that we have right here is new. And then same thing here with division, g of x divided by f of x, or g divided by f, all evaluated at x. When I've got things in the denominator, that's when I'm going to have some changes to my domain, some exceptions. Perform the indicated operation and state the domain. They don't have to be called f of x and g of x. Here I used f of x and h of x. You can call them really anything you want. So this symbol here for A just says I'm going to add f of x and h of x. F of x comes first, where f of x is x squared plus 3x minus 18, and h of x is x minus 3. Most of these functions will be quadratic or linear. They don't have to be. We've done all kinds of polynomials at this point. So I'm going to take f of x. What is f of x equivalent to? X squared plus 3x minus 18. And I'm going to add that to h of x. I'm just kind of following this recipe on the left-hand side here. And h of x is x minus 3. If you feel better rewriting that without the parentheses, you can. Either way, because it's addition, none of the signs change or anything, so it doesn't really affect any of my signs. And then I'm just looking for like terms like we've been doing for years. I only have 1x squared, but I've got 3x and x. 3x plus 1 gives me 4x minus 18. Minus 3 gives me a minus 21. Since this problem doesn't have any variables, it's not going to create any exceptions for values of the domain. So my domain will just be all real numbers. We can write all real numbers in different notations. So just to, bring those back up. Could also be rewritten as negative infinity to infinity. If I write it in interval notation, or negative infinity to x to positive infinity if I were to write it in inequality notation, just so we can see a variety and be reminded that they all mean the same things. So the next one is subtraction. Make sure you follow the right order. So I have h of x first this time. When I have subtraction, it's really important that I use my parentheses. And then minus f of x. That subtraction in front of parentheses means I need to go through and I need to think of that as either distributing a negative 1 through to everything in the parentheses or going through and changing all the signs in everything that comes after the subtraction. So I have x minus 3 minus x squared minus 3x and plus 18. Find like terms and simplify. So I've got a minus x squared, no like terms there. An x and a minus 3x gives me a minus 2x. Minus 3 and a plus 18 will give me a plus 15. Because I have no variables in the denominator, I'm not going to have any exceptions to my domain, so it's just going to be all real numbers. Hopefully you can notice that the math here is just the same that we've been doing since, I don't know, when you start doing like terms. Math 1, maybe? Before? I don't know. But the notation is new, and the stuff we do next is going to be new. All right, so C is an example of multiplication. The f of x function comes first, and multiplied by the h of x function. I'm just going to distribute through. If you appreciate using the box here to kind of sort your terms, you absolutely can. This is a great tool, especially when you start getting a lot of terms. Sometimes it can be confusing to make sure you don't miss any of them. So either way that you want to do it, x squared times x is x cubed. X squared times negative 3 minus 3x squared. Multiply through 3x times x is 3x squared. 3x times negative 3 is minus 9x. Negative 18 times x. And negative 18 times negative 3, I think, is 54. And then we just look for like terms. Works the same exact way if you prefer the box. And then I just look for like terms. So I have a minus 3x squared plus 3x squared. Well, that's going to cancel. Minus 9x minus 18x gives me a minus 27x, and then a plus 54 at the end. Let me move that up for you. A, B, and C seem pretty benign. We get to D, division, and we actually will need to use some of our Math 2 skills for factoring. Let's see. So h of x goes on top, and then f of x goes on the bottom. Now I can't divide, I can't reduce this until I've put it in factored form. X minus 3 can't be factored. Just a linear expression. But the denominator can be factored. So if you like to use your product sum x, you can use that as a tool. Now remember, we've kind of gotten used to factoring in a couple of different ways. But when I have a quadratic trinomial, we talk about if the coefficient of x squared is 1, then I can use my kind of simpler, faster way to factor. I don't have to go through the entire process. So I'm going to give it two numbers and multiply negative 18 and add to 6. I'm sorry, add to 3. I'm getting ahead of myself. And the answer is 6 and negative 3. This will give me an x plus 6 and an x minus 3. This only works when the denominator is not 0. So I create this condition. Whatever's in the denominator can't be 0. So we've done this a couple times in the past where what values of x would make the denominator 0, and those are going to become exceptions for my domain. So I haven't actually done all the simplifying yet, but I'm going to switch tactics here and look at my domain. So in my denominator, I know that if I have x plus 6 and I set that equal to 0, that gives me a value of negative 6. So if I were to plug in negative 6 into here, I'd get 0. 0 times something is 0. I can't divide by 0. It's undefined. And then same thing here for the other factor. Any factor that has a variable. So my domain changes because I have a variable in the denominator. A little more work. Kind of brings us back to topic 2. I still have to go through and reduce this answer. So I do have a factor on top x minus 3 and a factor on bottom x minus 3. On top, that just leaves me with 1. And on bottom, it leaves me with x plus 6. That's my simplified expression. Any questions that I can help with on D? Nah. All right. So we have a lot of operations in math, right? Addition, subtraction, multiplication, division, exponents, radicals, all kinds of stuff. This is a new operation. It's called composition. And we have a lot of different, we have a symbol for everything, right, in math. This is a small open circle, which is different than a dot for multiplication. A composite function is when we apply a function to another function. Function composition can be written in 2 different ways. This can be written as f with a composition symbol g evaluated at x, or we can use parentheses, f evaluated at g of x. Both of them mean f composed with g at x. Yes, order matters. So for example 2, we're going to compose f with g of x and g with f of x. For f of x is x squared plus 2 and g of x is x minus 3. It's easy, especially in our writing, to kind of interchange what these look like. Like, I know some of our writing is a little bit more bubbly than other people's writings. And so this little empty circle is really important because it means something entirely different than just a closed dot, which is multiplication. So just something to be aware of in your writing. So evaluate a function at a function. Imagine this, if you will. Let's say you are going to put your money into some low risk stock option. All right. And they've created some kind of a predictor for how much money they think you're going to make in 10 years. Right. So you put your money into some kind of stock option and they've got a formula that's going to tell you how much money you're going to make. And then you know you're going to take that money, you're going to reinvest it into a different stock option. So you're taking your money, you're putting it in, and then you're taking that outcome and you're putting it into something else. That's what function composition looks like. So I have the function f of x. And I have the function g of x. Instead of evaluating f at x, I'm going to evaluate f at g of x. Right? So I'm doing this one first. F at g of x. So this was f of x. I took out the x and I'm replacing the other function. So I'm color coordinating mine. Maybe it'll help you follow along. The f of x function was x squared plus 2. But I'm no longer plugging in x. Now I'm plugging in g of x. So I replace x with g of x on the left side. And then on the right side, I'm going to replace x with the g of x expression, x minus 3. This is the new part. The rest of it's just order of operations. So let's just make sure that we can take that in for a minute. So I've replaced the input with a new function. So instead of x, I replaced my notation with g of x and my expression with x minus 3. I just kind of substitute those in. And then I'm just going to multiply it out and simplify. X minus 3 quantity squared is always written twice. X minus 3 times x minus 3. I'm just going to multiply that out. X squared minus 3x minus x plus 9 plus 2 at the end. Oh, come on. And I combine like terms. And I get a new function. This is f of g of x, which can also be written f of g of x. They're the same. Two different ways to write it. F of g of x, or f composed with g of x. The problem says to do it both ways. Compose f of g of x and g of f of x. So we're going to do the other one on this side too. So the next one, I want to plug f of x into g of x. Well, I know g of x is x minus 3. But I'm going to take out the x. I like to just leave a space to start. And I'm going to replace it with f of x. So I'm plugging blue into red. Whatever's on the inside goes into the outside function. So when I evaluate g at f of x, I replace x with x squared plus 2. Questions here? Okay. Then I just perform whatever operation I've got. In this case, I just combine the 2 and the 3. And I'm left with x squared minus 1. Example 3 is very similar to example 2. It's just using the other notation, right? But they're equivalent. So this says f composed with g of x. This says f composed with g of x. They say the same thing, all right? So I could rewrite this if I wanted to. Let's see, if I color coordinate, I'll make this one blue again, and this one red again. So I could write this as f of g of x, or I could rewrite it as f of g of x. They're equivalent. I'm going to pause there and give you a chance to work those out. I know we've only done one example, but I think the operation is not too complicated. So take 2 or 3 minutes and try to work these ones out on your own. Okay. We'll go ahead and take a look and see how it went. So the f of x function is 2x minus 5. Nope, 2x minus 5. I lost my x. And I want to evaluate f at g of x. So I'm going to basically take out the x's, and I'm going to replace it with g of x notation on the left-hand side and the equivalent of g of x on the right-hand side. Let's see, that gives me 16 minus 2x minus 5. And you can write the answer either way as long as you're very aware that they're equivalent. I like to write my answer in whatever way they asked the question. So I'm going to use the composition symbol here instead of parentheses. So when I take g of x and I plug it into f of x, I get negative 2x plus 11. So you're always plugging what's closest to x into the outside function. What's closest to x into the outside function. All right, so I take f of x and I plug it into g of x. So g of x is 8 minus x. But I want to evaluate g at f of x. So I'm going to replace my notation on the left-hand side, and I'm going to replace the other part of my function on the right-hand side. I've got subtracting some parentheses here, so we'll make sure that we distribute that through. So g of f of x is negative 2x plus 13. How does this feel? Does it feel okay? Any questions that I can help with or give clarity to? So example 2 and 3 were composing a function with a function, and these last examples that I have here are composing functions evaluated at a number. You'll notice the functions are the same, just have different directions. So here I want to remember my same composition rule. I'm going to start on the inside and work my way out. So evaluate f of g of 1 when f of x is equal to x squared plus 2 and g of x is equal to x minus 3. Okay, so I'm going to evaluate g at 1. So g of x is equal to x minus 3, and I'm going to plug in g of 1. Now this composition question says evaluate f at g of 1. Well, g of 1 now is just negative 2. So I'm going to evaluate f at negative 2. So I take a number, I plug it into the inside function, I get a new output. That output goes into my outside function. So again, you're always going to start on the inside. Bless you. G of 1. So I take 1, I plug it in G, I get out negative 2. And then I take negative 2 and I plug it in for this piece, G of 1, and evaluate f at negative 2. So I evaluate the inside function, then I take that output and evaluate the outside function. And come up with a total answer. This could also be written f of g evaluated at 1. So that's another way to write it, using that composition symbol. And then we've got just one more to do for practice. Okay, so this one, just a different notation. Another example. I have to do what's closest to the number first. So I'm going to start with f of negative 3. Then I'll take the inside and I'll plug it back into the outside. Yes, order matters. Composition is not commutative like addition and multiplication. I rewrote it using parentheses. For me, this makes more sense in my brain than this, but you just got to pick what works for you. So I like to write it like this when I can, with parentheses. Because now instead of f of negative 3, I'm going to plug in negative 11 into g. That whole minus negative thing turns into a positive. And when I evaluate g at f, or g of f of negative 3, I get 19. Any questions that I can answer on this? That is the entirety of the lesson. Kind of like one new concept and then utilizing what we already know from previous math classes. So hopefully you found it reasonable.